Lesson 5.4, multiple angle identities. So in this lesson, we're going to learn a few more identities, double angle, and power reducing identities. First, we'll talk about the double angle identities. We have those for sine, cosine, and tangent. Yes, there are three different ones we have for cosine. But if you look at the right portions of those equations for cosine, it's fairly easy to see, if we use the Pythagorean identities, how we can go from one of these forms to the other. Now we're going to discuss the power reducing identities. These are going to be very similar to the half angle identities. So we have one for the sine, cosine, and tangent. If we were trying to write the half angle identity for the sine, we would take the square root of each side of the equation, giving us a plus or minus the square root of this quantity. And rather just being a value of u, if it was a half angle, it would be u divided by 2, which means our value, the angle value in our expression on the right, instead of 2u, this would just be u. So you should have the power reducing and half angle identities on your sheet, and you can compare those equations. They're going to be very similar. Example 1, we want to prove that the sine of 2u is equal to 2 sine u times cosine u. So we want to prove the double angle identity for the sine function. We're going to use stuff from the previous lesson. So if we start with the sine of 2u, we can break that up into the sine of u plus u. Now we would use the stuff from lesson 3 where we had the sine of a sum. Now if we use that formula and break this apart, we get the sine of u times the cosine of u plus the sine of u times the cosine of u. We have the same term, so we can combine this into 1 by adding the coefficients of 1. Thus we get 2 times the sine of u times the cosine of u. So we use the sine of a sum identity from the previous lesson to show why the double angle identity for sine is equal to 2 times the sine of u times the cosine of u. Example 2, we want to prove the identity cosine to the fourth of theta minus sine to the fourth of theta equal to the cosine of 2 theta. So we're going to start with the left side of our equation, cosine to the fourth power of theta minus sine to the fourth power of theta. We're going to use ideas of factoring from algebra because this is a difference of two squares. We could break this up into cosine squared theta minus sine squared theta times the quantity cosine squared theta plus sine squared theta. So using the difference of squares patterns, we break this up, cosine squared theta plus sine squared theta. We know that is going to be a value of 1, the Pythagorean identity. So we're left with cosine squared theta minus sine squared theta. And looking at this portion, this is one of the double angle identities for the cosine of 2 theta. So cosine of squared theta minus sine squared theta simplifies down to the cosine of 2 theta. So to start this problem, we use ideas of factoring, the difference of two squares. Broke this down. We use the Pythagorean identity to simplify the cosine squared of theta plus sine squared theta into 1, leaving us with cosine squared theta minus sine squared theta. Looking at our identities, this is one of the three forms for the cosine of 2 theta, which we simplified it down into. Example 3, we want to solve sine of 2x equals cosine of x on the interval from 0 to 2 pi. So the first thing we have to do is use a double angle identity for sine of 2x and rewrite this expression. Sine of 2x is equal to 2 times the sine of x times the cosine of x, and that is equal to the cosine of x. So now if we're going to try to solve this equation for x, we can get all of our terms on one side of the equation, so we would subtract cosine of x to the left side. So now we have 2 times the sine of x cosine x minus cosine x equal to 0. Looking at both these terms, we can use ideas of factoring out the common term of cosine x. So if we factor a cosine x out in front, that is going to leave us with 2 times sine of x minus, if we take a cosine x out of this term, we still have a value of 1 left, equal to 0. So now we're going to set each of our factors equal to 0 using the zero product property. So set cosine of x equal to 0 and set 2 sine of x minus 1 equal to 0. So now we have the cosine of x equal to 0 and the sine of x equal to 1/2. So thinking on our unit circle, what angle measures give us a cosine value that is equal to 0? Well, the cosine of theta is equal to 0, or the cosine of x is equal to 0 when x is equal to pi over 2 and 3 pi over 2. And then we're looking for where the sine of x is equal to 1/2. The sine of x is equal to 1/2 at an x value of pi over 6 and at 5 pi over 6. So bringing back the unit circle, solving for those x values that make our original equation true. So if we would plug any of these values in for x into the equation for sine of 2x equal to cosine x, it would give us a result that is true. Example 4, we want to solve the equation the cosine of 2x equal to sine x on the interval from 0 to 2 pi. So the first thing we need to do in this case is rewrite the cosine of 2x using a double angle identity. So out of the 3 options, we want to pick one that we can rewrite the cosine of 2x so that it has an expression in terms of the sine function. The reason we know we want to use the sine function is that if we look at the other side of our equation, it's in terms of sine. So we need to use an expression to rewrite the cosine of 2x in terms of sine. So using the double angle identity, we rewrite this as 1 minus 2 times sine squared x equal to sine x. Next, we would get all of our terms on one side of the equation. I chose to take both of these terms and move them to the right side of the equation, just so that my coefficient in front of my sine squared function would be positive. So now we have 0 equal to 2 times the sine squared x plus sine x minus 1. Next, we're going to try to factor this expression at the right. It might be a little difficult for us to see how this is going to factor. So we can set sine of x equal to y and rewrite this expression so that it looks like something we've factored in the past. So now this would be 0 equal to 2y squared plus y minus 1. Now we want to factor this quadratic. So if we try to factor 2y squared plus y minus 1, that breaks down into 2y minus 1 times the quantity of y plus 1. Now using the zero product property, we set each of these factors equal to 0 to solve for y. So we get y equals 1/2 and y equals negative 1. Now we can go back and substitute sine of x in for y. So we know that the sine of x is equal to 1/2 and the sine of x is equal to negative 1. Now we go and use our unit circle to come up with the x values that are going to make this statement true. So we're trying to find where our y values on the unit circle are equal to 1/2. That occurs at x values of pi over 6 and 5 pi over 6. And then we also want to determine using the unit circle where our y values are equal to negative 1, and that occurs at 3 pi over 2. So if we would plug pi over 6, 5 pi over 6, or 3 pi over 2 into our original equation that we started with, which was the cosine of 2x equal to the sine of x, that would give us a result that is true.